Good afternoon all. Hope you have enjoyed your lunch. So I am Arnab Goswami. I am working with Professor Vijay Krishna Das. I will be talking about some sources that are fundamentals resources for on-chip photonic computing using photonics. Now when we talk about quantum computer, we talk about qubit. So instead of simply 0 or 1, this qubit is a superposition of 0 and 1 states, and at the same time we can have entanglement. By entanglement I means these two qubit you cannot separate them. Now using these two properties we can effectively use up this thing to speed up our computation. Now what will be physical realization of this thing? In 2000 Di Vincenzo gave us some criteria. These are the criteria required for a qubit to do computation in a physical platform. So we should be able to define them, we should be able to measure them, and we should be able to manipulate them. Now the most fundamental question is, how many qubits do we need? As we went through the talk in the morning about noisy quantum computers, in the environment we do have noise, and that noise also affects our qubit. So this is a Google's roadmap in 2018. So what they are saying, if you want to have some useful error corrected quantum computation, you need more than 1 million qubit. Now you need this 100 to 1000 physical qubits to represent one logical qubit on which you will perform the computation. For practical implementation, we need to have scalability such that we can go up to 1 million qubit, and we should have our efficient error correction scheme. Now at the present moment, people are transitioning towards the near term applications from the classically simulatable, and they are showing some quantum supremacy as of now. Now there are many physical particles whose properties can be leveraged to do quantum computation. Now at the present moment, superconducting based qubit, they are leading the race because it is easy to produce qubit and high gate fidelity. But on the other hand, if you see, the qubit temperature operations is order of 15 millikelvin, it is a cryogenic temperature, and the coherence time is on the order of 200 and 300 microsecond. In spite of that, this at the present moment, last year IBM reported more than 1000 qubit processor. So the challenge of this community is that make this quantum process scalable towards more than 1 million physical qubit. On the other hand, if you see the photonic qubit, you can do photonic qubit operation at room temperature, and photons do not interact with other photon. What are the advantage? So photon decoherence only comes from loss, but due to the same time this can give some negative things because you cannot have 2 qubit gate. So now my 2 qubit gate are probabilistics. So you need more resources. But through classical integrated photonics, people have demonstrated more than thousands optical devices on a single chip. So people realized, okay, this is my scalable system, we can take the challenge to make it quantum and go to this more than 1 million physical qubit. Now these people have started later. So at the present moment, the one company from Candela from France, they have demonstrated 6 qubit processor. Now over the years, the potential of the photonics has been proven by bulk optics, that people have understood, okay, photonics has the potential and you can perform this quantum computation. But as you can see from the figures, it is a room size experimental setup. This is not scalable at all. So if you want to scale it, you have to put all these devices within the chip. Now when you talk about this photonic integrated circuits, there are many materials available at the present moment, but the most preferable materials are the silicon. The fundamental advantage is that this is CMOS compatible, means whatever electronics we fabricate and the same matured fabrication process technology can be used to manufacture this silicon photonics chip, and we need electronics to control the photonics, and same electronics we can build monolithically on a same chip. So you can have electronics and photonics on a same chip, and obviously we can have photon pair generation in this silicon photonics platform. Now, let us see what do you mean by single photon. So, if you see, if my ideal source is there, so each time in that when it emits, it will have only one number of photon source, but this is the ideal scenario. In real life, we won't get that, we have to approximate through some physical process. So, one of the ways is that if you have a two-level system excitation, so when electron jumps from this conduction band to the valence band, photon emits, but in reality there are imperfect collection efficiency. As a result, some of the time you won't get photons. So, as a result, for n equals to 0, your probability increases. The other way people thought, okay, you take a classical lasers and you attenuate up to single photon level, but it is a Poissonian statistics. That means, if you reduce it too heavily, many times you won't get any photon, few times you will get single photon, and a few times you will get more than 2 photons. So, this distribution is also not very helpful. The other way we can do, we can take a classical lasers and we can do light matter interaction through a nonlinear media, and we can generate photon pairs. So, the difference is that instead of one photon, I have 2 photons here, and their different colors means they are different in frequency. Now, if you see what is the probability of photon number for each of these photons, you will get these kind of things, where for n equals to 0, still the probability dominates. That means most of the time we won't get anything. But the advantage here is that because we are getting 2 photons that are separate in frequency, we can herald them. What I mean by that? We can separate this through a frequency selective filters, we can detect one photon, and that time we only take the distribution, because these 2 photons are generated together. And if we do this conditional probability on this when it is detected, it more looks like to this ideal photon source. So, this is what our photon source for the practical realization. Now, how we generate them? So, the fundamental thing is that polarization is a nonlinear function of electric field, because you see these higher order susceptibilities are there. So, when you excite these higher order susceptibilities, you can generate new frequencies. So, unfortunately for silicon, the second order susceptibility is 0. So, you have to excite this chi3, this chi3 is very low. So, you have to have very high amount of electric field. Now, this is a process, that is a 4A mixing process. So, when you launch high intense pump to excite this low chi3 through a silicon photonic waveguide, you will have 2 other photon pairs, signal and needler, and they have to follow this energy conservation and the momentum conservation. Because we are using this high intense pump to excite this low chi3, our pump power after the generation is still 10 to the power 10 times higher than the generated signal and needler. Now, we want to do operation on this signal and needler at the next stage, but we do not need this pump. So, we have to block this. So, we need something called this pump rejection filter, and this pump rejection filters has to be demanding, because it has to suppress this high intense pump by more than 100 dB, and it has to add minimum insertion loss over this signal and the Hitler. Now, in 2016, the Silverstone et al., they proposed how the architecture of a large scale silicon photonic processors will look like. So, first, as we discussed, we should have a photon source followed by the palm removal filters. Now, when we have this signal and Hitler, what we have to do? We have to manipulate them. Now, we need series of passive and active optics, but after this manipulation, we need to detect these photon pairs to get some measurements, to get some information. So, we have to detect them, and ideally this control and feedback electronics should be fabricated on the same chip. Now, if you see the present status, over the last 2 decades of extensive research on silicon photonics, these passive and active optics are almost matured. These matured device libraries are available for many foundry, and the single photon detectors and control feedback electronics at the present moment for most of the demonstration, they are being used off the chip, but few demonstrations are going on to make on chip. And the most fundamental requirement on the photon source and the palm removal filters that people have demonstrated a few part, but still development is necessary. So, my focus is on the photon sources and the palm removal filters. Now, I will talk about first the photon source. So, this is the cross section of a physical waveguides, where we have this 3 layer. This first layer is the silicon, second layer is oxide, and another is silicon, and the top is also by silicon dioxide. Now, the refractive index of the silicon is 3.47, it is more than the surrounding cladding things. So, we can have the light guidance here through the total internal reflection. So, you can have your optical mode here. Now, this is for a waveguide. So, we can make a resonator kind of structure through this waveguide such that at resonance we can have a intensity build up inside, because what we want to have a larger pump such that we can excite the Chi3. Now, if you see, this is the transfer function of these devices. So, whatever dip you are seeing, that dip are nothing but the resonances. So, it is resonances within the cavity. So, at the output you will get a drop. So, if you zoom one of these resonances, you will see there is a intensity build up compared to this bus waveguide within the ring, and that is what we will be using for our photon pair generation. So, if you launch a pump corresponding one of the resonances, your photon pairs signal and idler will be generated corresponding to the other resonances. So, for any resonance, the one of the important thing is that the quality factor. It defines how much loss presents within the device. So, our photon pair generation rate is depends on the input power, because if you launch high input power, your signal and idler generation will be more, and it is q to the power 3. But unfortunately, this is if you increase the power more, your loss will be increased. So, as a result, quality factor will decrease and your photon pair generation rate will also decrease. So, we have to investigate them in physically what are the process happening within the device. So, this is a cross sectional image of the waveguides. So, you see that the side wall things are having some roughness. So, that is why you will have some propagation loss. Now, when you launch high power, because of the Carr effect, we have the refractive index as a refractive index will be also a function of the power, and other important process that happens with the silicon is that two photon will combinedly excite one electron from the valence band to the conduction band, because this for the silicon band gap is 1.1 electron volt and 2 energy at 50 nanometer can exceed that band gap energy. So, as a result, this whatever light is coming that are getting lost, and further it will generate the free carriers, and these free carriers will also absorb the light. So, you have two consecutive loss, first is due to that and second is due to that, and these free carriers will change the refractive index as well, and in this process my heat will be generated. So, as a result refractive index will be modified. So, there are so many things are happening when you put high power in the resonator devices. Now, we model them and we have seen the what are the effects this happens. So, this is a experimental characterization of a ring resonator. So, if you see, as you increase your input power, the output power is not just getting changed, at the same time its shape is getting also distorted. So, what is actually happening? So, we model them and we have found that if you sweep from your wavelength from left side to the right side and right side to the left side, both the time you will get different transmission value. So, a bistable behavior exists within the ring resonator. So, this is what is the transmission look like. So, if you come from the left side, you will follow this black curve, and if you come from this outside, you will follow this red curve. And corresponding to that also, this within the ring, the amplified power also will be low. You can see, like if you come from this left hand side, this will follow the black curve. So, as a result your power generation will be more compared to if you come from this left hand curve. So, as a result, when you want to do this photon pair generation, you have to be in this point to get the advantage of this bistable solutions. Now, let us talk about the palm reaction filters, because this is the most challenging part. Now, for the palm reaction filter, we have working with these devices. This is a distributed Bragg reflector. So, this is a grating, a periodic grating in the waveguide length. This is the 3D same images. Now, if you launch a power here, some of the power will reflect and some of the power will transmit depending on the transmission of wavelength. So, in the transmission you will see some power will be dropped and that will come at the reflection. We want to use that device for a palm reaction filter, but the fundamental challenge here is that this is the reflection. So, this reflection propagates at the input side. So, if you directly just put this device, so this reflection will come this side and this will disturb my photon sources. So, that is what we do not want. So, we have redesigned this distributed Bragg reflector in a slightly different way. So, what we have done? We have checked like okay, depending on the waveguide width, there are different number of modes present in the waveguide. So, we have came up with this design like suppose okay, input waveguides is waveguide width is low where it supports only this mode 1. Now, I am doing the reflection in the higher order waveguide where I have these two modes, mode 1 and mode 2, and the reflection is happening in the form of mode 2. Now, when the reflection is coming at the input, because this input only supports mode 1, it won't be coming to the input side. As a result, your input source will be protected from this palm reflection. So, this is the higher order mode. You can see as it propagates to the input side, it gets radiated. So, your source will be protected. Now, we integrated them together, photon source followed by palm reaction filter. So, this is my source. I have generating this signal and idler here, and when it is passing through this palm reaction filter, at the output we will have signal and the idler. So, this we have fabricated from a commercial silicon photonics foundry, and this is the microscopic image. So, our device of interest is the bottom one where we have microring resonator followed by 2 stage of distributed Bragg reflector. So, if you zoom this microring resonator, this is the device looks like. So, this is the faint waveguide, and on the top you can see this is the ring, and this is the layer for hitting the microring resonator for tuning the resonances, and this is 2 micron away from the waveguide layer, and this is the distributed Bragg reflector. Now, this is the device spectrum that we measured. So, these are the deep you are seeing, this is the resonance coming from the microring resonator, and this is the big deep, this is coming from the distributed Bragg reflector for the palm reaction filter. So, we pump our resonator corresponding to this wavelength such that we can have pairwise generation of the photon pairs. So, when we launch this pump before we have amplified through an amplifier. Now, the fundamental problem with the amplifier is that when you amplify it adds this amplified spontaneous emission, this noise. So, if you see my signal and idler will be generated here. So, my noise to signal ratio will be degraded. So, we have to put a palm rejection AAC rejection filters after this before launching into that, and because of this sufficient was not what we demand. So, we have to use additional band pass filters here. Now, as we expected that as you increase the input power, your resonance is getting affected. So, as a result corresponding to this power level, my photon generation shape is also changing, and for this highest input power where I have the sharp changes. So, you see this is the wavelength we are tracking from the left side and the right side, and you can clearly see from the left side when you are tracking this my photon generation rate is higher. So, we have to work in this regime such that we can maximize our generation rate. Now, I come to the summary. We have modeled the nonlinear effects in silicon that affects the photon generation rate, and we have designed and demonstrated a novel palm reaction filter that can reflect the palm not to the input side, it can be radiated. And in case of this bistable generation, we have shown that the solution needs to be chosen carefully. Now, this is the photon generation part. Now, where it will be used? So, the first thing is that like this boson sampling. So, what we do here, we send all these photon pairs through a interferometric circuits, and at the end we measure this output. So, this output distribution that is it is a classical hard problem. So, you can by measuring this distribution you can get some quantum computational advantage such that quantum simulation you can do quantum random number generation. The last part is that photon is different from this qubit. So, we can do a encoding of the qubit where in the first, if I have these 2 waveguides and my photon is on the top part, that is my 0 state, if my photon is in the lower part, that is my 1 state, and we can have a cluster state of things where we can do universal quantum computation. So, in a nutshell, photonics has the potential to reach 1 million qubit in next decades that some companies are targeting. Thank you.